A spacecraft glides through the vast emptiness of space, its surface scarred by the relentless barrage of micrometeoroids. But instead of catastrophic damage, the hull begins to mend itself, tiny cracks sealing, dents smoothing, and structural integrity restored as if by magic. This isn't a scene from a sci-fi blockbuster. It's the future of space engineering made possible by self-healing materials. These aren't just materials, they're living systems capable of thinking, adapting, and repairing themselves in the harshest environments imaginable. Today, we're diving into the science and potential of this revolutionary technology, exploring how it's poised to transform the way we explore the cosmos. From extending the lifespan of spacecraft to reducing the risks of long-duration missions, self-healing materials are rewriting the rules of space travel. Join us as we uncover how these futuristic innovations are paving the way for safer, more efficient, and truly groundbreaking space exploration. So, what exactly makes self-healing materials so special? At their core, these materials are designed to imitate nature's incredible ability to repair itself. Think about how your skin heals after a cut or scrape. Self-healing materials work in a similar way, but on a molecular level. The secret lies in their structure. Some of these materials are embedded with tiny microcapsules, almost like microscopic bubbles filled with a healing agent. When damage occurs, these capsules burst open, releasing their contents to fill cracks or gaps and restore the material's integrity. Other types rely on dynamic chemical bonds, which are bonds that can break and then reform under certain conditions. Imagine a zipper that can unzip and then zip itself back together. That's essentially how these bonds work. Now, why is this so groundbreaking for space engineering? Space is one of the harshest environments imaginable. From micrometeoroid impacts to extreme temperature swings and relentless radiation, spacecraft face constant threats that can lead to wear and tear, or worse, complete failure. Self-healing materials could be the game changer here. Instead of waiting for a crack to grow or a component to fail, these materials can autonomously address the damage as it happens, potentially extending the lifespan of spacecraft and reducing the need for costly repairs or replacements. But it's not just about durability, it's about redefining what's possible. By understanding the molecular mechanisms behind these materials, scientists and engineers are unlocking new ways to design systems that can thrive in the most extreme conditions. Whether it's a satellite orbiting Earth or a rover exploring the surface of Mars, self-healing materials could ensure that these technologies remain operational far longer than ever before. So, what kinds of self-healing materials are being developed specifically for space? That's where things get even more fascinating. From polymers to metals and even ceramics, researchers are exploring a wide range of materials, each with its own unique way of repairing damage. But before we dive into those specific types, let's take a closer look at how these materials are tested and validated for use in space. After all, what works in a lab on Earth might behave very differently in the vacuum of space or under the intense radiation of deep space. The journey from concept to reality is a complex one, but the potential payoff is enormous. By harnessing the power of self-healing materials, we're not just solving problems, we're opening up entirely new possibilities for exploration and discovery. And as we continue to push the boundaries of what's possible, one thing is clear: the future of space engineering is going to look a lot more resilient. Self-healing materials are revolutionizing space engineering, and they come in a variety of forms, each tailored to tackle specific challenges in the cosmos. Let's start with self-healing polymers, which are leading the charge in this groundbreaking field. These polymers are particularly advanced, capable of repairing cracks or damage on their own, making them ideal for protective coatings and structural components. Imagine a spacecraft's exterior that can fix itself after a scratch or a small fracture, ensuring the integrity of the mission without requiring costly repairs or risky spacewalks. But the innovation doesn't stop there. Researchers are pushing the boundaries even further by developing self-healing metals and ceramics. These materials are designed to endure the extreme conditions of space. Think intense radiation, drastic temperature swings, and the relentless vacuum. Take shape memory alloys, for example. These remarkable metals can remember their original shape and return to it after being bent or deformed. This ability makes them incredibly valuable for spacecraft hulls, solar panels, and even the suits astronauts wear. Imagine a solar panel that can withstand micrometeoroid impacts by simply reshaping itself, or an astronaut suit that repairs a tear on its own during a mission. The possibilities are truly game-changing. Each type of self-healing material brings its own strengths to the table. Polymers excel in flexibility and ease of application, while metals and ceramics offer unparalleled durability in the harshest environments. Together, they share a common goal: to extend the lifespan of space missions, reduce maintenance costs, and enhance safety for astronauts. And when it comes to one of space engineering's most persistent challenges, micrometeoroid impacts, these materials could be the key to a more resilient future in space exploration. Out in the vast expanse of space, there's a danger so small it's easy to overlook, yet so fast and destructive it can jeopardize entire missions. Micrometeoroids, tiny fragments of rock and metal, often no larger than a grain of sand, race through space at speeds exceeding 30,000 miles per hour. At that velocity, even the smallest particle can punch through critical components of a spacecraft, leaving behind cracks, punctures, or worse. The International Space Station has faced this threat firsthand, with its windows and solar panels bearing the scars of micrometeoroid impacts over the years. These tiny strikes might seem insignificant, but in the unforgiving environment of space, even a minor breach can lead to catastrophic consequences like air leaks, system failures, or even mission-ending damage. This is where self-healing materials step in as a revolutionary solution. Imagine a spacecraft hull or solar panel that can detect a micrometeoroid strike and instantly begin repairing itself, sealing cracks or filling in punctures before they cause any harm. This isn't science fiction, it's a capability already being tested in labs around the world. For long-duration missions like those to Mars or beyond, self-healing materials could be the difference between success and failure. In deep space, where repair missions are impossible and every component must endure for years, these materials could provide a level of resilience that's never been possible before. They wouldn't just patch up damage, they'd ensure the spacecraft remains functional and safe, no matter what the cosmos throws its way. But the potential of self-healing materials doesn't stop at micrometeoroid protection. These advanced materials could also play a critical role in enhancing thermal protection systems, ensuring spacecraft can withstand the extreme temperature swings of space. From the blistering heat of direct sunlight to the freezing cold of shadowed regions, space is a thermal roller coaster, and keeping a spacecraft system stable is no small feat. Next, we'll explore how self-healing materials could tackle this challenge, offering a new layer of safety and reliability for the next generation of space exploration. When we think about the challenges of space travel, one of the most critical hurdles is surviving the extreme temperatures that spacecraft encounter. Picture this: during re-entry, the exterior of a spacecraft can reach temperatures as high as 1,600 degrees Celsius, hot enough to melt most metals. Meanwhile, in the vast emptiness of deep space, temperatures can plummet to nearly 270 degrees below zero. These extreme fluctuations place immense stress on materials, leading to cracks, wear, and even catastrophic failures over time. This is where self-healing materials come into play. Imagine a heat shield that doesn't just withstand the blistering heat of re-entry, but actively repairs itself when damaged. Self-healing ceramics, for instance, could autonomously fill in cracks caused by thermal stress, maintaining their structural integrity even under the most intense conditions. These materials work by incorporating tiny capsules or fibers that release a healing agent when cracks form, effectively sealing the damage before it spreads. The implications of this technology are enormous. Not only would it enhance the safety of astronauts and spacecraft, but it could also drastically reduce the need for frequent maintenance. Traditional heat shields and insulating layers often require costly inspections and repairs after each mission, but self-healing materials could extend their lifespan, saving both time and resources. But the potential doesn't stop at heat shields. Insulating layers within spacecraft could also benefit from self-healing properties. In the harsh environment of space, even the smallest breach in insulation can lead to significant heat loss or gain, jeopardizing the delicate balance needed to sustain life and equipment. Self-healing materials could automatically patch these breaches, ensuring consistent temperature control and reducing the risk of system failures. This innovation isn't just about surviving the extremes, it's about thriving in them. By integrating self-healing materials into thermal protection systems, we're not only solving a problem but also paving the way for longer, safer, and more efficient missions. And as we continue to push the boundaries of space exploration, these advancements could be the key to unlocking new possibilities, from extended lunar habitats to crewed missions to Mars. Now, let's shift our focus to another critical area where self-healing materials could make a transformative impact: the design and construction of space habitats. How might these materials help us create living environments that are not only durable but also adaptable to the unpredictable challenges of space? Let's dive in. Imagine living in a habitat on Mars where the airlock seals itself after a micrometeoroid strike, or the walls of your home patch up cracks caused by relentless dust storms. This isn't science fiction, it's the future of space habitats made possible by self-healing materials. As we look toward establishing permanent bases on the Moon, Mars, or even in orbit, one of the biggest challenges is creating living environments that can endure the brutal conditions of space. From extreme temperatures and radiation to micrometeorite impacts and corrosive dust, the materials we use will need to be as resilient as they are advanced. Self-healing materials could revolutionize how we build these habitats. Picture a Martian base where the walls are embedded with smart polymers or microcapsules filled with healing agents. When a crack forms, whether from a dust storm or the constant stress of temperature fluctuations, the material activates, sealing the damage before it becomes a life-threatening issue. The same technology could be integrated into critical systems like airlocks and life support, preventing leaks and ensuring the safety of astronauts. This isn't just about repair, it's about resilience. By reducing the need for constant maintenance, self-healing materials could make long-term space colonization not only feasible but sustainable. And the benefits go beyond structural integrity. Imagine the psychological impact on astronauts knowing their habitat can adapt and recover from damage. Instead of worrying about a small crack leading to catastrophic failure, they can focus on their missions, research, and survival. This technology could be the key to transforming space habitats from fragile outposts into robust, self-sustaining homes. It's a game-changer for humanity's next giant leap into the cosmos. But habitats are just one piece of the puzzle. Next, we'll explore how self-healing materials could protect astronauts themselves, starting with the suits they wear to survive the unforgiving environment of space. Spacewalks are one of the most awe-inspiring yet perilous aspects of space exploration. Astronauts floating against the backdrop of Earth or the vastness of space represent humanity's boldest steps into the unknown. But behind the breathtaking visuals lies a harsh reality. Every spacewalk carries inherent risks. Current astronaut suits, while advanced, are vulnerable to tears, punctures, and wear over time. Even the smallest breach could lead to catastrophic consequences in the vacuum of space. Enter self-healing materials, a game-changing innovation that could redefine the safety and functionality of these suits. Imagine a scenario where a micrometeoroid strikes an astronaut's suit during a mission. Instead of facing a life-threatening emergency, the suit's material instantly repairs itself, sealing the breach and ensuring the astronaut's safety. This isn't science fiction, it's the promise of self-healing technology, but the benefits don't stop at safety. Traditional suits are bulky and restrictive, designed to protect but often at the cost of mobility and comfort. Self-healing materials could change that. By incorporating flexible, adaptive polymers, these suits could offer greater freedom of movement, reducing the physical strain on astronauts during long-duration spacewalks. Picture an astronaut on a future mission to Mars where extended periods outside the spacecraft will be unavoidable. A self-healing suit wouldn't just protect them, it would make their work easier, more efficient, and far less exhausting. This kind of innovation isn't just about survival, it's about enabling humanity to thrive in the most hostile environments imaginable. And let's not forget the long-term implications. Self-healing materials could drastically reduce the need for repairs and replacements, cutting down on mission costs and logistical challenges. For missions to Mars and beyond, where resupply from Earth isn't an option, this durability could be the difference between success and failure. It's not just about making space exploration safer, it's about making it sustainable. Now, while astronaut suits are a critical application, the potential of self-healing materials extends far beyond personal protection. Consider the satellites orbiting our planet, quietly powering the technologies we rely on every day. What if these satellites could repair themselves too? Let's explore how self-healing materials could revolutionize satellite technology and extend the lifespan of these essential systems. Satellites are marvels of engineering, designed to withstand the harsh conditions of space, but even the most advanced materials eventually succumb to wear and tear. Radiation bombardment, extreme temperature fluctuations, and the relentless impact of micrometeoroids all take their toll. Over time, these factors degrade critical components, shortening the operational lifespans of satellites and forcing costly replacements. But what if satellites could repair themselves? Enter self-healing materials, a groundbreaking innovation that could revolutionize how we approach space technology. Imagine a satellite's solar panels, essential for powering its systems, being struck by tiny space debris. In the past, such impacts would create microcracks, reducing the panel's efficiency and eventually rendering it useless. But with self-healing materials, these panels could automatically repair the damage, maintaining their performance for years longer than ever before. This isn't just a theoretical concept. Researchers are already developing polymers and composites that can heal cracks caused by micrometeoroid impacts, ensuring satellites remain operational far beyond their current lifespans. The implications are enormous. For commercial satellite operators, longer-lasting satellites mean significant cost savings, as fewer launches would be needed to maintain services like global communications or Earth observation. For scientific missions, extended operational periods allow for more data collection, enabling deeper insights into our universe. And let's not forget the environmental benefits. Fewer launches mean less space debris and a reduced carbon footprint. But the potential doesn't stop at solar panels. Self-healing materials could be integrated into other critical satellite components, such as thermal protection systems or structural frames, ensuring they remain resilient against the relentless challenges of space. By addressing the root cause of degradation, this technology could transform satellites from fragile, finite tools into durable, long-term assets. Now, as we look ahead, the next frontier for self-healing materials lies in propulsion systems. These systems, essential for maneuvering satellites, face their own set of challenges that self-healing materials might just be able to overcome. When it comes to space exploration, propulsion systems are the beating heart of every mission. They're what get us off the ground through the atmosphere and into the vast expanse of space. But here's the catch: these systems are under constant stress. From the intense heat of rocket engines to the pressure of carrying thousands of gallons of fuel, every component faces wear and tear that could jeopardize a mission. That's where self-healing materials step in, not just as a futuristic concept, but as a practical solution to some of the most persistent challenges in space engineering. Imagine the fuel tanks that store the propellant needed for a rocket's journey. Over time, tiny cracks can form in the tank's structure, leading to potential leaks or even catastrophic failures. With self-healing materials, these cracks could be automatically repaired, preventing fuel loss and ensuring the tank remains intact throughout the mission. The same principle applies to rocket nozzles, which endure extreme temperatures and pressures during liftoff and flight. Self-healing composites could absorb this stress, repairing themselves in real time to maintain peak performance. This isn't just about improving reliability, it's about redefining what's possible in space travel. Consider the environmental implications as well. Traditional propulsion systems often require extensive maintenance and replacement of parts, which can generate waste and increase costs. Self-healing materials could significantly reduce this burden, making space missions more sustainable and cost-effective. By minimizing the need for repairs and extending the lifespan of critical components, we're not just advancing technology, we're also taking a step toward a more environmentally conscious approach to space exploration. And that's a win for both engineers and the planet. But the benefits don't stop there. Enhanced reliability means fewer mission failures, which translates to safer journeys for astronauts and more successful outcomes for scientific endeavors. Whether it's a Mars rover or a crewed mission to the Moon, self-healing materials could be the key to unlocking a new era of exploration. And as we look to the future, the potential applications are almost limitless. From interplanetary travel to deep space probes, these materials could help us push the boundaries of what we thought was possible. So, what does this mean for the future of propulsion systems? It's not just about making them stronger or more durable, it's about making them smarter. With self-healing technology, we're not just fixing problems as they arise, we're preventing them altogether. And in the unforgiving environment of space, that could make all the difference. One of the most pressing challenges in space engineering today isn't just about reaching further into the cosmos, it's about dealing with the mess we've already left behind. Space debris, a chaotic swarm of defunct satellites, discarded rocket stages and fragments from collisions, now orbits our planet at staggering speeds. This growing cloud of debris poses a serious threat to both current and future missions, making it harder to launch new satellites or maintain existing ones without risk of collision. But here's where self-healing materials come into play, offering a potential game-changer for reducing this orbital clutter. Imagine a satellite that can repair itself after being struck by a tiny piece of debris, or a spacecraft that can patch up microcracks caused by extreme temperature fluctuations in space. By integrating self-healing materials into the design of satellites and other space infrastructure, we could significantly extend their operational lifespans. This means fewer satellites would need to be replaced over time, reducing the number of new objects launched into orbit and, in turn, cutting down on the amount of space debris generated. It's a solution that not only enhances efficiency but also addresses a critical environmental issue. But the benefits don't stop there. Self-healing materials can also be engineered to degrade safely at the end of their life cycle. Instead of lingering in orbit as hazardous debris, these materials could break down into non-threatening components that either burn up upon re-entry or dissolve harmlessly. This approach aligns perfectly with the growing push for sustainable space exploration, where the focus isn't just on reaching new frontiers but on preserving the space environment for future generations. It's a step toward cleaning up our cosmic backyard while ensuring that humanity's journey into space remains responsible and forward-thinking. Of course, developing materials that can heal themselves while withstanding the harsh conditions of space is no small feat. The challenges are immense, from creating compounds that can repair damage in the vacuum of space to ensuring these materials remain stable under extreme radiation and temperature swings. Yet the potential rewards make this a challenge worth tackling. By solving these problems, we're not just advancing technology, we're taking a crucial step toward a cleaner, safer, and more sustainable future in space. While the potential of self-healing materials in space engineering is undeniably exciting, turning this vision into reality isn't without its obstacles. One of the biggest challenges lies in ensuring these materials can withstand the extreme conditions of space. Think about it. Spacecraft are exposed to everything from intense radiation to drastic temperature swings, not to mention the constant bombardment of micrometeoroids. For self-healing materials to be effective, they must not only survive these harsh environments but also repair themselves quickly and reliably, even when subjected to such relentless stress. Another major hurdle is achieving rapid healing times. In the vacuum of space, there's no room for slow repairs. A material that takes hours or days to heal a crack could leave a spacecraft vulnerable to catastrophic failure. Researchers are working tirelessly to develop materials that can heal almost instantaneously, using mechanisms like chemical reactions or embedded microcapsules that burst open to seal damage as soon as it occurs. But balancing speed with durability is no easy task. Materials must remain strong and stable even after multiple healing cycles. Then there's the issue of longevity. Space missions often last years, if not decades, and materials need to maintain their properties over those extended periods. Imagine a self-healing material that works perfectly for the first few years but degrades over time, losing its ability to repair itself. This could jeopardize the entire mission. Scientists are exploring ways to design materials that not only heal but also retain their structural integrity and functionality for the long haul. Cost and scalability are also critical factors. Even the most advanced self-healing materials won't make an impact if they're too expensive or difficult to produce on a large scale. The goal is to create materials that are not only effective but also affordable enough for widespread use in space engineering. This requires innovative approaches to manufacturing, as well as interdisciplinary collaboration between materials scientists, engineers, and industry experts. The good news: these challenges are driving some of the most exciting breakthroughs in the field. Researchers are leveraging cutting-edge technologies and creative thinking to push the boundaries of what's possible. And one of the most promising areas of innovation lies in nanotechnology, which is playing a pivotal role in advancing self-healing materials. By working at the molecular and atomic level, scientists are unlocking new ways to design materials that are not only tougher and more resilient but also smarter, capable of detecting and repairing damage in ways that were once the stuff of science fiction. At the heart of self-healing materials lies a groundbreaking field, nanotechnology. This isn't just about making things smaller, it's about redefining how materials behave at their most fundamental level. By working at the nanoscale, where dimensions are measured in billionths of a meter, scientists are unlocking the ability to create materials that can sense, respond, and even repair themselves. Think of it like giving materials their own immune system, one that activates the moment damage occurs. One of the most exciting applications is the use of nanoparticles embedded within the material itself. These microscopic particles act as tiny repair agents, lying dormant until they're needed. When a crack forms, they spring into action, releasing chemicals or filling gaps to restore the material's integrity. It's a bit like how your body sends white blood cells to heal a cut, but in this case, the process happens almost instantly and without human intervention. What makes this even more remarkable is the precision involved. Because nanotechnology operates at such a small scale, it allows for incredibly targeted responses. Imagine a spacecraft's hull detecting a microcrack caused by space debris and sealing it before it can grow into a larger problem. This level of sophistication could revolutionize how we approach durability in extreme environments, especially in space, where repairs are nearly impossible to perform manually. But the potential doesn't stop there. As researchers continue to refine these nanoscale systems, they're exploring ways to make self-healing materials even more versatile. Some are experimenting with materials that can heal repeatedly, while others are designing systems that adapt to different types of damage. It's a field that's evolving rapidly, and the implications for space engineering are nothing short of transformative. Now, let's shift our focus to how these self-healing materials could reshape the way we manufacture and maintain spacecraft. From reducing the need for costly repairs to enabling longer missions, the possibilities are as vast as space itself. Picture this: instead of launching every single bolt, panel, and beam from Earth into space, future missions could manufacture these components right in orbit. This isn't just a sci-fi dream. It's a practical solution to one of the biggest challenges in space exploration: the cost and complexity of transporting materials. Manufacturing in space could revolutionize how we build everything from satellites to space stations, and self-healing materials are poised to play a starring role in this transformation. Imagine a scenario where a 3D printer in orbit crafts a critical part for a space station. If that part gets damaged, say, from micrometeoroid impacts or extreme temperature fluctuations, it wouldn't spell disaster. Instead, the material itself could repair the damage thanks to self-healing polymers. These advanced materials aren't just tough, they're designed to recover from wear and tear autonomously, making them ideal for the harsh conditions of space. This capability opens up incredible possibilities. Think about constructing habitats on the Moon or Mars, where transporting materials from Earth would be prohibitively expensive. With self-healing materials, we could build durable structures that maintain their integrity over time, even in environments where traditional materials would fail. And it's not just about longevity. These materials could also simplify the construction process itself. Components could self-repair during assembly, reducing the need for costly and risky repairs by astronauts. But the impact goes beyond just engineering. The economic implications of self-healing materials in space manufacturing are enormous. By reducing the need to launch heavy payloads from Earth, missions could become far more cost-effective. Every kilogram saved on launch weight translates to significant savings in fuel and logistics. Over time, this could make space exploration more accessible, enabling more frequent missions and even commercial ventures like space tourism or asteroid mining. What's more, the ability to manufacture and repair structures in orbit could extend the lifespan of existing space infrastructure. Satellites, for example, could be upgraded or repaired using self-healing materials, reducing the need for replacements and cutting down on space debris. This approach doesn't just save money, it also promotes sustainability in an environment where resources are scarce. As we look to the future, it's clear that self-healing materials could be a game changer for space manufacturing. By enabling the creation of durable, self-sustaining structures, they'll help us push the boundaries of what's possible in space. And as we'll see next, the ripple effects of this technology could extend far beyond the stars. Space exploration has always been an expensive endeavor, with budgets stretching into the billions for even a single mission. But what if the materials used in spacecraft could repair themselves, cutting down on costly repairs and replacements? That's where self-healing materials come into play, offering a game-changing solution to one of the biggest hurdles in space engineering: cost. By integrating these materials into spacecraft, we could drastically reduce the financial burden of maintenance, making space missions more affordable and sustainable in the long run. Think about the current process. When a spacecraft suffers damage, whether from micrometeoroids, extreme temperatures, or wear and tear, it often requires expensive repairs or even replacement parts. These fixes aren't just costly, they're time-consuming, delaying missions and adding layers of complexity. But with self-healing materials, many of these issues could be resolved autonomously. A crack in a spacecraft's hull, the material seals itself. Abrasions from space debris, the surface regenerates. This not only slashes repair costs but also extends the lifespan of spacecraft, making missions more efficient and less reliant on frequent maintenance. The ripple effect of this technology could be enormous. Governments, which currently shoulder the bulk of space exploration costs, could allocate their budgets more effectively, funding more missions or investing in new technologies. Private companies, from satellite operators to asteroid mining ventures, would also benefit as the reduced costs lower the barrier to entry. Even individuals with aspirations of space travel might find their dreams more attainable as the economics of space tourism become more feasible. Suddenly, the final frontier isn't just for massive organizations with deep pockets, it's a realm of possibility for a much broader range of players. But the economic advantages don't stop there. The reliability of self-healing materials could also attract more investors to the space industry. Imagine a world where spacecraft are less prone to catastrophic failures, where missions have a higher likelihood of success. This kind of dependability is a magnet for funding, encouraging both private and public sectors to pour resources into space ventures. It's a win-win. More investment leads to more innovation, and more innovation leads to even greater advancements in space technology. The economic implications of self-healing materials are as expansive as the universe itself. By reducing costs, increasing efficiency, and boosting reliability, this technology has the potential to transform space exploration from a high-stakes gamble into a more accessible and sustainable endeavor. But as we marvel at these possibilities, it's also worth considering the ethical questions that arise. How do we balance the benefits of self-healing materials with their potential risks? What responsibilities come with creating materials that can outlast traditional systems? These are the kinds of questions we'll tackle next as we delve into the ethical considerations of this groundbreaking technology. As we marvel at the potential of self-healing materials to revolutionize space engineering, it's crucial to pause and consider the ethical implications that come with such advancements. Every leap in technology carries with it a responsibility to ensure that its benefits are distributed fairly and that its risks are carefully managed. For self-healing materials, this means tackling questions about who gets access to these innovations, how they impact our environment, and what safeguards are in place to prevent misuse. Take equitable access, for example. While self-healing materials could drastically reduce the costs of space missions by minimizing repairs and extending the lifespan of spacecraft, there's a risk that only well-funded organizations or nations could afford to harness this technology. This could widen the gap between spacefaring entities and those still struggling to enter the arena. Ensuring that these materials are accessible to smaller teams, developing nations, and educational institutions is vital to fostering a more inclusive future in space exploration. Environmental concerns also come into play. The production and disposal of advanced materials often leave a significant footprint. If self-healing materials rely on rare or non-renewable resources, or if their manufacturing processes generate harmful waste, we risk solving one problem while creating another. Researchers and engineers must prioritize sustainability, exploring ways to make these materials eco-friendly from production to end of life. Then there's the question of misuse. Like any powerful tool, self-healing materials could be exploited for purposes that go beyond their intended use, whether in military applications or other high-stakes industries. Establishing clear ethical guidelines and regulatory frameworks will be key to ensuring that this technology serves humanity's best interests rather than becoming a source of conflict or harm. By addressing these ethical challenges head-on, we can create a future where self-healing materials not only push the boundaries of what's possible in space engineering, but also uphold the values of fairness, sustainability, and responsibility. And speaking of pushing boundaries, let's shift our focus to how these materials could inspire entirely new mission concepts, opening doors to possibilities we've only begun to imagine. Imagine a spacecraft venturing into the crushing atmosphere of Venus, where temperatures soar high enough to melt lead, or a probe diving beneath the icy crust of Europa, braving radiation and sub-zero cold. These are the kinds of missions that once seemed impossible, not just because of the engineering challenges, but because the risks were simply too great. But with self-healing materials, we're now looking at a future where these extreme environments could become accessible. Picture a spacecraft equipped with materials that can repair themselves after being battered by corrosive gases or micrometeoroid impacts. Suddenly, the impossible starts to feel within reach. One of the most exciting possibilities is how self-healing materials could revolutionize interstellar exploration. Think about it, once a spacecraft leaves our solar system, there's no turning back. If something breaks, there's no way to send a repair crew, but what if the ship could fix itself? Self-healing materials could be the key to ensuring that interstellar probes survive the decades-long journey to distant stars, maintaining functionality even in the harshest conditions of deep space. This isn't just science fiction anymore, it's a tangible goal within our grasp, and it's not just about survival. These materials could enable entirely new mission concepts that push the boundaries of what we thought was possible. For instance, imagine a rover designed to explore the sulfurous volcanoes of Io, one of Jupiter's most hostile moons. With self-healing components, it could endure the intense heat and corrosive gases, continuously repairing itself to keep exploring. Or consider a probe sent to the subsurface oceans of Enceladus, where it would face freezing temperatures and immense pressure. Self-healing technology could ensure it keeps functioning, gathering data that could unlock secrets about the potential for life beyond Earth. The implications are staggering. By removing the limitations imposed by material degradation, self-healing technology could open up entirely new frontiers in space exploration. It's not just about making missions safer or more reliable, it's about redefining what we can achieve. The universe is vast, and with self-healing materials, our ability to explore it could become just as limitless. As we look to the stars, it's clear that this technology isn't just an incremental improvement, it's a game changer. And speaking of game changers, the development of self-healing materials isn't something any one nation or organization can tackle alone. It's a challenge that calls for global cooperation, bringing together the brightest minds and most advanced resources from around the world. This brings us to the next chapter in this story, the role of international collaboration in advancing self-healing materials. When it comes to groundbreaking advancements like self-healing materials, no single country holds all the answers. That's why international collaboration is absolutely essential. Think about it, space engineering is one of the most complex and resource-intensive fields out there. By working together, nations can combine their strengths, share cutting-edge research, and pool resources to tackle challenges that might otherwise be insurmountable for a single entity. This global effort isn't just about sharing the workload, it's about accelerating progress so that humanity as a whole can benefit. Imagine scientists from Japan contributing their expertise in nanotechnology, while engineers from the United States bring their experience in aerospace design, and European researchers add their knowledge of advanced polymers. Together, they're not just building materials, they're building the future of space exploration. But collaboration doesn't stop at simply sharing ideas. It also involves creating global standards and best practices to ensure these materials are used safely and effectively. After all, self-healing materials will play a critical role in missions that push the boundaries of human ingenuity, missions where even the smallest failure could have catastrophic consequences. By establishing international guidelines, we can make sure that every country, every company, and every space agency is on the same page when it comes to deploying these technologies. This kind of cooperation could also open the door to more ambitious projects, like joint missions to Mars or the construction of lunar bases, where self-healing materials could be a game changer. And let's not forget the economic and societal benefits of this collaboration. By sharing the fruits of this research, nations can democratize access to space technology, making it more accessible to emerging space programs and private companies. This could level the playing field, allowing more players to contribute to the next chapter of space exploration. It's a reminder that the challenges of space aren't just technical, they're also about bringing people together to achieve something greater than the sum of its parts. Now, as we look ahead, it's impossible to ignore how self-healing materials could shape the future of space tourism. Imagine a world where private citizens can travel to space as easily as booking a flight across the globe. The stakes are high and safety is paramount. Self-healing materials could be the key to making this vision not just possible but practical. Imagine boarding a spacecraft knowing that the very materials it's made of can repair themselves mid-flight. It sounds like science fiction, but with self-healing materials, this could soon be the reality for space tourists. As the space tourism industry takes off, ensuring passenger safety and comfort becomes a top priority. Self-healing technology offers a groundbreaking solution, addressing some of the most critical challenges in space travel. One of the biggest concerns for space tourism is the risk of micrometeoroid impact. These tiny but fast-moving particles can cause significant damage to spacecraft hulls, posing a threat to both the vehicle and its passengers. Self-healing materials could change the game here. Picture a spacecraft hull that automatically seals cracks or punctures caused by these impacts, preventing air leaks and maintaining structural integrity. This kind of resilience would not only make space travel safer, but also reduce the need for costly repairs or emergency measures during a flight. But it's not just the exterior of the spacecraft that stands to benefit. Inside, self-healing materials could enhance passenger comfort in ways we've never seen before. Imagine seats, flooring, or even cabin walls that repair themselves after wear and tear, ensuring that every flight feels as pristine as the first. This durability would be especially valuable in the harsh environment of space, where materials are subjected to extreme temperatures, radiation, and vibrations. By maintaining their functionality and appearance, these materials would create a more luxurious and reassuring experience for travelers. The ripple effects of this technology could be enormous. By making space travel safer and more comfortable, self-healing materials could help attract a broader audience to the space tourism industry. families, adventure seekers, and even those hesitant about the risks might feel more confident about booking a trip beyond Earth's atmosphere. This influx of interest could drive innovation and investment, accelerating the growth of the industry and making space tourism more accessible to people around the world. As we look ahead, the potential of self-healing materials extends far beyond tourism. Their applications in deep space exploration could redefine how we approach long-duration missions where reliability and durability are absolutely critical. But that's a story for the next segment. For now, it's clear that self-healing materials are poised to transform space tourism, turning what was once a distant dream into a safe, comfortable, and thrilling reality. When we think about deep space exploration, the challenges are as vast as the cosmos itself. Missions to Mars or even further into the outer reaches of our solar system demand spacecraft that can withstand the test of time, literally. These journeys aren't just a matter of months, they span years, even decades, and in the harsh environment of space where help is millions of miles away, every crack, every fracture, every tiny failure could spell disaster. That's where self-healing materials step in. Picture a spacecraft equipped with materials that can detect damage and repair themselves autonomously. A micrometeoroid strikes the hull. No problem, the material seals itself, maintaining structural integrity. Over time, radiation degrades a critical component. The material regenerates, ensuring the mission stays on track. This isn't just about keeping the ship intact, it's about keeping the crew safe and the mission viable, no matter how far from Earth they venture. But the impact of these materials goes beyond the technical. Imagine what this means for inspiring future generations. The idea that we can build machines capable of healing themselves in the void of space is nothing short of revolutionary. It's the kind of innovation that captures imaginations and fuels dreams. Think about the young minds watching a Mars rover land or a probe send back images from the outer planets. Now add the layer of self-healing technology and suddenly the narrative shifts. It's not just about exploring the unknown, it's about creating tools that adapt, survive, and thrive in the most unforgiving environments. This blend of resilience and ingenuity could spark a new wave of interest in science, engineering, and exploration. It's a reminder that the future of space travel isn't just about reaching new destinations, it's about redefining what's possible. And let's not forget the broader implications. Self-healing materials could set a precedent for how we approach sustainability and longevity in technology. If we can create materials that repair themselves in space, what's stopping us from applying similar principles here on Earth? From infrastructure to consumer electronics, the ripple effects could be profound. Space exploration has always been a catalyst for innovation, and self-healing materials might just be the next big leap. As we look to the stars, we're not just building spacecraft, we're building a legacy of resilience and creativity that could shape the future of humanity, both in space and at home. The development of self-healing materials isn't just a scientific breakthrough, it's a spark of inspiration that could ignite the imaginations of future generations. Think about it, every time we push the boundaries of what's possible, we plant seeds of curiosity and ambition in the minds of young scientists, engineers, and dreamers. Imagine a child today watching a spacecraft repair itself in the harsh vacuum of space and thinking, "I want to be part of that." That's the power of innovation. It doesn't just solve problems, it creates a legacy of possibility. Self-healing materials are more than a tool for space exploration. They're a symbol of human resilience and creativity. They remind us that even in the face of immense challenges, we can find solutions that not only endure but also evolve. This technology is a testament to our ability to adapt, to think beyond the limits of today, and to build a future where the impossible becomes routine. And here's the thing, the ripple effects of this innovation go far beyond the lab or the launch pad. By tackling the toughest problems in space engineering, we're setting the stage for discoveries that could transform life on Earth. The same principles that allow a spacecraft to repair itself could revolutionize industries like healthcare, construction, and transportation. It's a reminder that the challenges we face today are opportunities for the next generation to redefine what's possible. So, as we look to the future, the legacy of self-healing materials isn't just about the technology itself. It's about the mindset it inspires. It's about fostering a culture of innovation where failure isn't an end but a stepping stone to something greater. It's about encouraging young minds to dream big, to explore the unknown, and to believe that even the stars aren't out of reach. Now, let's take a moment to reflect on what we've learned about this groundbreaking technology. From its potential to extend the lifespan of spacecraft to its ability to inspire future innovators, self-healing materials are more than just a scientific marvel. They're a glimpse into a future where resilience and creativity reign supreme. As we wrap up our exploration of self-healing materials, it's clear that this groundbreaking technology is more than just a futuristic concept. It's a game-changer for space engineering. Picture this: spacecraft that can repair themselves mid-mission, habitats on distant planets that withstand extreme conditions, and satellites that last decades longer than ever before. These aren't just dreams, they're realistic possibilities within our grasp, thanks to the incredible advancements in self-healing materials. What makes this innovation so transformative is its ability to tackle some of the toughest challenges in space exploration. Think about the harsh environment of space: extreme temperatures, radiation, micrometeoroid impacts, all of which can wreak havoc on traditional materials. Self-healing materials offer a solution, not just by enduring these conditions, but by actively recovering from damage. This means safer missions, longer-lasting equipment, and the potential to explore farther and deeper than we ever thought possible. But the impact doesn't stop there. Imagine missions to Mars where habitats can repair cracks caused by shifting terrain, or lunar bases that maintain their structural integrity despite constant bombardment from space debris. These materials could even pave the way for entirely new mission concepts, like spacecraft designed to autonomously adapt to unforeseen challenges. It's not just about fixing what's broken, it's about redefining what's achievable in space exploration. As we look to the stars, self-healing materials remind us of something profound. Innovation knows no bounds. Every leap in technology brings us closer to unlocking the mysteries of the cosmos, and this is no exception. The future of space engineering is brighter than ever, and it's thrilling to imagine what lies ahead. Thank you for joining us on this journey into the future of space technology. If you're as excited about the potential of self-healing materials as we are, let us know in the comments what aspect of this technology inspires you the most. Don't forget to like, subscribe, and share this video with fellow space enthusiasts. Until next time, keep dreaming of the stars because the future is closer than you think.